Ever wished your code could handle surprises a little more gracefully? Well, today we're diving into a way to build that flexibility right into a program's DNA. Row polymorphism. You've sent over some fascinating articles by Max Bernstein, and I gotta say, this idea of making data structures as adaptable as a jazz solo has me intrigued.
It's a really elegant approach to a common programming challenge. To really appreciate it fully, though, I think we should probably start with a fundamental concept in type systems. Most Hindley Milner, or HM for short.
Yay. Like the sound a brilliant programmer makes when they've cracked the code. Okay, I'm all ears. What's so special about this HM?
Think of HM as like a superpowered spell checker for your code. In languages like standard ML, it analyzes your program and automatically figures out the type of each piece of data, whether it's a number, a string of text, or even a complex structure. This automatic type checking, it's what we call type inference.
So like a spell checker catches typos, HM catches type errors before they become bugs. That sounds incredibly useful, especially for someone like me who's prone to making typos.
Precisely. And the beauty of HM really lies in its elegance. It strikes this balance, being expressive enough to handle a wide range of programming scenarios, yet efficient enough to quickly analyze your code without getting bogged down. It's this balance that has made HM incredibly influential in the world of programming language design.
It's like having a super smart assistant who not only organizes your code, but also makes sure you're using the right tools for the job.
Exactly. Now, imagine you're working with a database of customer information. Each customer might have different fields. Some might have a phone number, others might have an email address, and some might have both. This is where the concept of records becomes essential, these collections of named values. And it's also where HM's strict rules about types can feel a bit limiting.
I see. It's like trying to sit square blocks into round holes. If HM insists, each record has to have the exact same fields.
A perfect analogy. Let's say you're writing a function to process these customer records. In a dynamically typed language, you wouldn't need to worry too much about the specific fields in each record beforehand. But HM, with its, love for order, wants to know the exact structure of these records. This is where things get tricky. How do you represent something as flexible and unpredictable as a database record within a system that thrives on order and predictability?
That's where row polymorphism comes in, right?
Right.
This is where we ditch those rigid blocks and bring in something more
Yeah.
fluid.
Absolutely. Row polymorphism is all about bringing that much-needed flexibility to HM. It allows us to work with records that might have varying fields, making our code much more adaptable to real-world data. It's like giving HM a taste of that jazz improvisation you mentioned earlier.
Okay, now you're making me think about music. How does this whole row thing work? Does it involve tiny drum solos within the code?
Not quite, but I appreciate the enthusiasm. Imagine rows as building blocks for record types. Each row is like a blueprint, holding pairs of names and their corresponding types, like name paired with string or age paired with integer. But here's the key. Rows have a special rest field, which is like a wildcard slot in our blueprint.
So it's like saying, here's what we know for sure, but there might be other stuff too.
Exactly. And it's this rest field that gives rows their flexibility. Let's say we encounter a new customer record with an unexpected field, like favorite ice cream flavor. Instead of throwing an error, our row can accommodate this new information thanks to that handy rest field.
So it's like having an extra drawer in a filing cabinet for anything that doesn't quite fit in the labeled slots. That's pretty clever. But with all this potential for extra stuff, how do we make sure things don't descend into chaos? How do we maintain some sense of order?
That's a great question. And it leads us to the concept of unification, which is essentially HM's way of making sure all our rows play nicely together.
Unification. It sounds almost diplomatic, like a peace treaty for record types.
That's a fantastic way to put it. Unification is all about ensuring that even with the flexibility of the rest field, our rows are still compatible, and that they can work together harmoniously within the type system.
Okay, I'm hooked. Tell me more about this peace treaty process. How does HM make sure these potentially chaotic rows can still collaborate effectively?
Well, imagine you have two rows that need to be unified, like two puzzle pieces we want to fit together.
Okay, I'm picturing it. One puzzle piece is our customer record, and the other is our function that's trying to process that record.
Precisely. Now, there are a few different scenarios we might encounter when trying to unify these rows.
Oh, this is where it gets interesting. Hit me with those scenarios. Let's see how HM plays peacemaker.
In the simplest case, both rows have the exact same fields, like two identical puzzle pieces. HM just makes sure their rest fields are compatible too, ensuring they stay in sync even if we add more fields down the line.
So it's like checking that both puzzle pieces have space for the same background image, even if we haven't filled it in yet.
Got it.
What about those times when the rows aren't identical?
That's where things get a bit more interesting. Imagine one row has all the fields of the other, plus a few extra. In this case, HM simply adds those missing fields to the smaller row, making sure they end up with the same rest field. It's like expanding one of our puzzle pieces to accommodate those extra details.
So no matter which row is bigger, HM finds a way to make them match up. It's like HM is a master puzzle solver, finding those connections to make everything fit.
Precisely. And the best part, this whole unification process is what unlocks the true magic of row polymorphism.
Ah, yes, the heart of our deep dive. We've built up the foundation, now let's see how it all comes together.
Remember how HM loves order? Well, row polymorphism is like giving HM the flexibility to work with a variety of record structures without sacrificing that love for organization.
So instead of needing a different function for each possible combination of fields in a record, row polymorphism lets us write one function that can handle them all.
You got it. It's like having a universal adapter for your code that works seamlessly with any record structure as long as it has the necessary fields.
That's incredibly powerful. It's like having a master key that can unlock any door in a building as long as it's designed to work with that key system. But how does this row polymorphism relate to other types of polymorphism in programming? Remember, Bernstein mentioned something called let-polymorphism.
That's a great question, and it shows you're really starting to connect the dots. Think of polymorphism as a spectrum of flexibility in how we write and reuse code. Row polymorphism gives us amazing flexibility when working with records, but let polymorphism takes it a step further.
Okay, so if row polymorphism is like a master key for records, is let polymorphism like a master key for any data type?
You're catching on quickly. Let's illustrate with an example. Imagine you have a function called double that simply doubles the value you give it. With let polymorphism, this function can work for integers, decimals, even more complex data structures, as long as the doubling operation makes sense for that type.
So it's like our double function just knows how to double regardless of the specific type of data it's dealing with. That's amazing. It's like having a universal translator for your code.
That's a great way to put it. And it's this power of generalization that makes let polymorphism so valuable.
This is all starting to click now. We've talked about HM, its love for order, the flexibility of rows, and the power of polymorphism. But I'm curious, are there different ways that HM actually figures out all these complex type relationships behind the scenes?
Absolutely. Bernstein touches on two key algorithms for type inference in HM, algorithm W and algorithm J. Think of them as two different but equally brilliant detectives trying to solve the same mystery.
Ooh, a detective analogy. I'm intrigued. Tell me more about these code sleuth.
Algorithm W is like the meticulous detective who examines every clue in detail, carefully piecing together the puzzle of your code's types. It's known for its elegance and clarity, making it relatively easy to understand and reason about.
So algorithm W is all about precision and taking its time to get things right. What about algorithm J? Is it the more intuitive, go with your gut type?
That's a great way to put it. Algorithm J is all about speed and efficiency. It uses a clever technique called unifying to quickly group together types that should be considered equivalent. It's like a detective who can see connections instantly, using their intuition to cut through the noise and get to the heart of the matter.
Interesting. So two different approaches, but with the same goal, making sure our code's types are all in order.
Exactly. Now let's shift gears a bit and talk about how HM, powerful as it is, can be extended to handle the complexities of real-world programming. One area where HM needs a little help is in dealing with recursion.
Recursion, those functions they call themselves. I've always found them a bit mind-bending. How does HM handle those without getting stuck in an infinite loop?
That's a great question, and it highlights one of the challenges in designing type systems for practical programming. To handle recursion, HM essentially uses a clever trick. It creates a placeholder type for the recursive function, allowing it to analyze the function's type even before fully understanding its inner workings.
So it's like saying, I trust you'll figure out your own type eventually, just promise me you'll be consistent.
Exactly. This trust but verify approach is crucial for making recursion work seamlessly within the structured world of HM. But the extensions don't stop there. Bernstein also talks about expanding HM to work with more complex data types beyond just simple numbers and text.
Right, because in the real world, data comes in all shapes and sizes. It's not always as simple as just numbers and letters. What kind of complex data structures are we talking about here?
Well, one common example is lists, which can hold sequences of elements. Think of a shopping list. You might have items like milk, eggs, and bread. HM can be extended to ensure that all elements in a list have the same type, guaranteeing consistency and preventing errors when working with these collections of data.
That makes a lot of sense. It's like saying, this is a grocery list, so everything on it needs to be a grocery item. It helps avoid those moments when you accidentally add a car to your shopping cart. But what about other ways of working with data, like pattern matching? How does HM ensure type safety when we're using patterns to extract information from data?
You're thinking like a true programmer now, always considering those edge cases. Pattern matching is incredibly powerful, but it can also introduce potential type errors if we're not careful.
Right, because if HM is expecting a certain type of data and we feed it something completely different, things could get messy quickly.
Exactly. But HM has a clever way of handling this. Let's say you're using a pattern to extract the first two elements from a list. HM will analyze that pattern and realize, aha, this pattern only makes sense if we're dealing with a list of data.
So it's like HM is reverse engineering our intentions, understanding the kind of data we're trying to work with based on the patterns we use. That's pretty impressive.
It is. And once HM understands the expected data type, it can then use that information to infer the types of variables within the pattern, ensuring everything is consistent and type safe.
So HM can handle even those more advanced programming moves, which is reassuring. This has been a fascinating journey into the world of type systems. We've covered so much ground, from HM's love of order and the ingenious flexibility of rows to the power of polymorphism and how HM uses its detective skills to keep our code in check.
It's remarkable, isn't it, how these concepts, which might seem quite abstract at first glance, have such a profound impact on how we write reliable and robust software.
Absolutely. We've gone from a basic understanding of types to exploring how we can make them adaptable to real-world data and complex programming paradigms. The elegance and thoughtfulness baked into these systems is impressive.
It really makes you appreciate the work that goes into designing programming languages that can be both powerful and safe to use.
It really does. After diving deep into this with you, I'm left with a sense of wonder about the future of type systems. What are your thoughts on where this journey might lead us?
That's a question I'm constantly pondering myself. I think we're only scratching the surface of what type systems can do. As software becomes increasingly complex, I believe type systems will play an even more crucial role in ensuring that our code is reliable, secure, and predictable.
It's exciting to think about what innovations are yet to come, all thanks to the foundation laid by these fundamental ideas. What stands out to you from all of this?
For me, it's the elegant way row polymorphism solves that challenge, of representing real-world data within a strict type system. It's a testament to the ingenuity of finding solutions that balance flexibility and safety.
That's a great takeaway. It's like finding that perfect harmony between improvisation and structure, both in jazz and in our code.
Exactly.
Well, this has been an enlightening deep dive into the world of row polymorphism and beyond. Thanks to your insights and the fantastic source material, I feel like I've gained a whole new appreciation for the hidden heroes that are type systems.
The pleasure was all mine. It's always a joy to talk about these fascinating concepts with a curious mind.
Until next time, keep your code clean and your data structures flexible.